Okay. So I hope everybody remember that 2 weeks ago we had a speaker from Peking University who told us about how situation about profinite completion of 3 manifolds. So it's my great pleasure today to introduce our today's speaker, Jimin Ma, who is going to tell us about situation in 4-dimensional manifolds, right, and profinite completions. Please go ahead.
Okay, so thank you. So first, I would like to thank Professor Zixi for the invitation, and it's my great honor to speak in this seminar. And in fact, so when I first studied something related to profinite completions of manifold groups, and I read the book by Professor Rebus and Zixi. Okay. So today I will talk about distinguished 4-dimensional geometries with profinite completions, and this is a short work with Zixi Wang, also from Fudan University. N-dimensional geometry X, and by this I mean in the sense of Thurston means a pair X and G. So here X is a simply connected n-dimensional smooth Riemannian manifold, and also with a Lie group action, or here the Lie group is such the G. And then, so of course we have some conditions. So for example, we assume the G action here is transitive and effective, and also isometric on the Riemannian group. And we also assume G is maximum among all such Lie groups X on the Riemannian manifold X, and this could be seen as some isometric group of certain Riemannian matrix. Okay, and then so I'm interested in something related to closed manifold. So we call the manifold that means the geometry X here. X is a pair, simply connected. So and then so we call manifold that means geometry X if it is the constant like this one. So gamma here is a discrete subgroup of the Lie group here with X fixed with X freely on the Riemannian manifold, and such that the manifold here it is just M. It has a finite volume, and as is well known in the 3-dimensional case, and Thurston classified all the 8 geometries, and it is well known that 3 manifold that means 6 among in the 8 geometries can be related as fibred space. And but today we will talk about the 4-dimensional case, and in 4-dimensional case, Quiz classified the 4-dimensional geometries in the sense of Thurston, and in total there are 19 classes of maximum geometries, and moreover with 1 class, including infinite many non-equivalent geometries. And also it is like the case of 3-dimensional manifold and a closed orientable for manifold with 8 geometries among the 14 class could be realized as a Seifert fibred manifold. Of course, here is a 4-dimensional Seifert manifold, and there are only 2 excepted ones, and which are flat. So here is a table of the class of 4-dimensional geometry, and so the first class is it is a finite group. So the universal cover are just the S4 and CP2 and H2 times H2. And in this case, the manifold has a finite fundamental group, and moreover there are only 7 manifolds. So in the viewport of profinite completions, we can ignore them. And the second one is the so-called geometry F4, and here H2 is just the 2-dimensional hyperbolic space, and the T here is the tangent space. So the geometry here is just the tangent space of the hyperbolic plane. And moreover, we mark here. So in this geometry, there are no closed for manifold. So here every manifold here admits some boundaries. So we don't talk about animal in today. So and the third type is just the Newton type. In three-dimensional case, there are E, 3, and near 3. But in four-dimensional, there are E4, near 4, and near 3 times E. And so near 4 and near 3 times E. So E is just the relay. And in these two cases, there are infinite many manifold. But for the flat one, there are only finite many orbifold and finite many manifold. And the first one is the Seifert type. So there are three types of geometries: SOL4 and MN, and SOL40 and SOL41. And moreover, so in this case, SOL4 MN, there are infinite many geometries. We will talk about we will talk a little more later. And then there are some product type. So these three type just so hyperbolic type times two sphere, and the three sphere type times the relay, and the three sphere times the replay. And here the manifold with these geometries are spherical manifold. So in other words, pi 2 or pi 3 is non-trivial. And then so this three type is a little difficult than these three types. Here is a three-dimensional hyperbolic space times the relay. This is the SL2 puta times the relay, and this is the hyperbolic plane times the replay. And here the manifold with these three types of geometries are spherical. So so in other words, everything of the manifold is determined by its fundamental group. So it is good examples to study profinite completions of their fundamental groups. Okay, and then the third type of product geometry is the real hyperbolic plane times the real hyperbolic plane, and this case is more difficult than these three types of geometries. And the most difficult of four-dimensional geometries among the native geometries in the sense of Thurston is the real hyperbolic geometry of dimension 4 and complex hyperbolic geometry of complex dimension 2. And in my viewpoint, this guy is the most difficult one among all of these one. Okay, among all of these geometries. And in fact, so in our work, so we almost have say nothing about these three types of geometries, but we work essentially on this type of geometries. So it you can see, and our proof depends on the previous result on two-dimensional geometry and three-dimensional geometries. And since the four-dimensional hyperbolic case here and here are too difficult for us right now. Okay, so right now we have 19 geometries in the sense of Thurston in four-dimensional. Okay, and we just give an example. It is just the geometry of SOI4MN And here it is just the semi-product here from the three-dimensional Euclidean space and the semi-product with the ray line. And so the matrix here is just the diagonal of this matrix. So such that E power A, E power B, and E power C are three distinct re-root of the polynomial here. So here we can normalize such that M and N are two positive integers. And then the fundamental group of a closed orientable SOL for Mn manifold here has the form of the semi-product. So the normal subgroup is such that J cube, and we still had the action of the integral group here. Okay, so here and so the action is just given by a metric here, the metric B with three distinct eigenvalues. And the three distinct eigenvalues are just E power A, E power B, and E power C. Okay, and in a particular case, that is, I mean, so when M equal to N, so then the geometry here is just the product geometry here. So here as source 3 is a three-dimensional geometry, and this is the ray line. So in this case, it is in some sense degenerate. So, and in general, so for different M and for many pairs of different M and N, so we have infinite geometries. So and then we just consider something about shift for manifold. This is just which is similar to the case of three-dimensional shift fibred space. Here, for manifold, it is shift fibred. I mean, it is the total space of a bundle here. So here M here is for manifold, and B is just closed to orbifold, such that the general fiber is 2 tau T2. Okay, and with so three-dimensional case is just the general fiber is just T1, that is a circle here, and the orbifold is also over the closed to orbifold. So we just take the fiber from T1 to T2. Okay, yeah. And just like the case of three-dimensional manifold, to describe our shift for manifold, there are some events which are similar to the case of three-dimensional shift fiber manifold. And we also have the local model of four-dimensional shift fiber manifold, and which for example locally. So and so remember here. So for four-dimensional shift fiber manifold, we have M4, which is for manifold, and we have also a two orbifold B. And we take a singular part of the two orbifold B, and then it has a neighborhood D. This is the constant space. This is just a constant space like this one. Here D2 is the unit disk in the reply, and then by a trivial discrete subgroup of G. So here, of course, G is just a finite group. And with fixed P the only fixed part of on the unit disk. On the unit disk, okay. And then, so we have another. So we extend the action G here from G is just GX on the unit disk to GX on the product from the torus and the unit disk here, which act on the product space here freely. And then so here it is just an orbifold, manifold, right? Okay. So for the base case, it is an orbifold, but here it is for manifold since G acts on this space freely. And then the part P here is it's non-singular if and only if G is trivial. Then in this case, so the neighborhood of P in B is just a disk, but in general it is a two orbifold. Okay. So in fact, there are three types of singular part in the two orbifold B. Okay. So the first case is just given by the action here. So remember here G is just a finite group which act on the reply. So and here which act on the reply just we take it just this action. So here and this action and this action are in the are the constant of the reply, which is the T2, that is the torus. So and in other words, so here these two guys give us T2 and this one give us a part in the reply. Okay, so and so here and the action of G on the manifold is like this one, and it's and this action is for so here we have the condition here. It's so the three numbers here, M and A and B here the great common divisor of them is just one. Then so the P here is the copart of the two orbifold, and the inverse of P is the torus, but it is a multiple torus of type M, A, and B. This is just this type of singularities is a typical singularities. Okay, and another case is the reflector. So here G here is a group with two elements. So and it on it acts on the replay, such the reflection here, and then we lift this action of G on here to the action on the torus times the disk. So then here P is just a reflector of the two orbifold B, and then so here the converse image of the two orbifold here is just the twist due to bond over the clean bottle K. So, and the third one is just the union, some sense the union of these two types of singularities. So since it is just the different group, so but anyway we can ignore it. So you can just remember this type of singularities, and this type of singularities is enough for our purpose. Okay. And so for example, for the simple case, so we can describe for manifold here of M here. It is a T2 bundle over a T2, and here, so here A and B are some matrices in SL2J, and Mn are two numbers, and here it is just the monodromy of two loops on the base. So since the base here is just a torus, and the fiber here is also a bundle. So and there is no singularities. So but in this case, there are some more drawing about the circles, essential circles in the base here. Okay, and then yeah, but anyway, so the fundamental group of the manifold here can be written down explicitly, and so it is generated by four elements here, L, H, S, and T. So for L, H are generated of the general fiber of the torus, and S and T are the lift of the generator of the base torus. And there are some relations here, and it is simple to get the presented here. Okay, so in anyway, so for the four-dimensional Seifert fiber space, we can write down its fundamental group explicitly, which is important in the study of its profinite completion. Okay. And then by classifying closed orientable for four-dimensional Seifert manifold using the four-dimensional Seifert event. So a Japanese mathematician connected this manifold to Thurston geometries, and so here is his theorem that M be a closed orientable for manifold, which is Seifert fibered over two epifold B. So if the base to epifold is spherical or bad, if and only if the manifold it means geometry here and here, and then if the base is flat, then the for manifold it means one full geometries here flat one and near 4 and then near 3 times the relay, or short times the relay. Okay, and then if the base is hyperbolic, then either the for manifold it means one full geometries this guy and this guy, or in other case, M is not geometry in the sense of certain. Or so in other words, so the lighting geometries in four-dimensional case it's not so powerful like the case in the three-dimensional case. And remember, so in three-dimensional case, so it is roughly say everything is determined by geometries. Or in other words, every manifold it means decomposition into some piece, and every piece is it means some geometries. But in four-dimensional case, there are many manifolds which does not it means any of these 19 geometries. And even though remember I have said the four-dimensional hyperbolic geometry and the two-dimensional complex hyperbolic geometry is difficult to study, but not every, but they are not so dominating in the case of three-dimensional manifold and three-dimensional geometries. Okay, and I believe so. All of you maybe know some, maybe very familiar with profinite completions and profinite groups. So maybe I should talk about this part very quickly. So, and for partial order, so a universal system is a family of sets of like this guy, and then we can take the universal system. So, and then we can define its universal limit like this guy. And for today's purpose, we just consider profinite completion. So, so here, and we just take XIB finite group and Phi group homomorphism. Then the resulting universal limited is a profinite group. Okay, and this is the definition of profinite group, and for our purpose, so we study discrete subgroup. We study the completion of we study profinite completion of a discrete group here. So And so the finite group here is just correspond to a finite indexed normal subgroups of a discrete group of a discrete group G. 也基数的这个fundamental group of a manifold. And then so the collection N of all of finite indexed normal subgroup of G here form a universal system. And then we can take its finite completion, which is given by this notation G hat. Okay. And yeah, so from G, and we get a G hat, which is such that it's a profinite completion. Okay, which is which is a compact Hausdorff totally disconnected and uncountable. If G is not a finite, I think so it is a topological group. Okay. Group G is rational finite if for every non-trivial element G G in this group. There is some finite index a normal subgroup N such that G here is not in this finite index normal subgroup. Okay, and this is important for the profinite completion of a group. So examples, for example, so the group here is rational finite, and free group is rational finite. Surface group is rational finite. And the fundamental group of closed spherical manifold is also rational finite. This fact depends on Pedman's solution of geometrization of manifold. And there are some examples which are not rational finite groups. For example, infinite simple groups or the famous Bohm-like solitary group here, BSMN, with this relation, then it is not a Bohm, which is not a rational finite group. And in general, it is not a rational finite. And also, there are some spherical manifold in dimension of digital 4, such that its fundamental group is not rational finite. This is very different from the case of three-dimensional case. Since in three-dimensional case, every the fundamental group of every spherical manifold is rational finite, but in four-dimensional case, there are some manifold, even though it is spherical, but its fundamental group is not rational finite. Okay. And so group G is rational finite if and only if we just consider all of finite index normal subgroup of G here, and the intersection is such the identity one. And also if and only if the nature map from G to its profinite completion is injective. Okay. And so I think I should skip something maybe. So if since for in general, so for G being a finite generator rational finite group, there is a one-to-one correspondence between a set of subgroup of G with finite index and a set of Y of our open subgroup of the profinite completion of it. And so from the discrete group here, we just take its closer, and in another direction, for subgroup Y, which is in finite, which is an open subgroup of the profinite completion. We just take the intersection of it with the original group G, and then it is then the map here it's one-to-one correspondence, and this preserves the index and so. Okay. So In general, if let G1 and B2 be two finitely generated abstract groups, then they have the same profinite completion if and only if they have the same set of profinite. They have the same set of finite constant. So, and another thing should introduce is the good. So, finite generated group G here is good if for our finite G model here, G models here A, and the nature homomorphism of coherent groups of the profinite completion, and the original group here is isomorphisms for any dimension n. And there are some examples. For example, finite generated function groups are good, and also extensions of good group by another good group is also good, and also so three manifold groups are also good, but this depends not only Peddman's solution of geometries and also on Ego and Weiss the solution of the so-called water fiber conjecture of hyperbolic manifold. And so for our purpose, so we use group, we use the property group good to show the group here is reduced finite. So here still could be G is a reduced finite good group, and there is a surjective map from map here H to G, and such that the kernel of the map here is reduced finite and finite generated. Then the bigger group here H, it is reduced finite. Okay, and so and there are some standard result on reduced finite. For example, polycyclic bifinite group are reduced finite, and any finite generated linear group is also reduced finite. And then the corollary of all above is that M be a closed orientable for manifold. Manifold with one of 16 geometries, I mean one of the 19 geometries above. Then the fundamental group of it is reduced finite. So since the fundamental group of it is reduced finite, then we can study its profinite completions. Okay. And the standard question is that for a discrete group here and to determine which property of G, or maybe which property of the manifold with fundamental group G is determined by its profinite completion. Okay. So, and in a class of in a certain family of G of groups, a reduced group G is called profinite in this class of groups if if the G here can be distinguished in this class of groups by its profinite completions. And of course, profinite flexibility means the rigidity fields. In other words, maybe there are two different groups, G1 and G2 in this class, but they have the same profinite completions. And also, if the class is the collection of all finite generated reduced finite group, and G is just absolutely profinite rigid if in the above the definition it is rigid. Okay, and so for example, free groups we don't know whether free group is profinite rigid in the set of all finite generated reduced finite groups. Okay. And some other examples, for example, by Baumslag, for gamma 1 and gamma 2 is just the semi-product of groups of this very simple one, but these two groups are not isomorphic, but they have the same profinite completions. In other words, so important groups are not profinite digits, okay, even in a set of important groups, okay. And in the case of three-dimensional manifold, and Caligari, Friedman, and Walker asked whether the fundamental group of the three manifold is determined by its finite quotient, okay, or equivalent by its profinite completions. And there are some positive results, for example, by Gardner he showed profinite digits in the snappy sentence. So Gardner using computer shows no two hyperbolic manifold in a snappy sentence of more than 70,000 manifold have the same finite quotient. Okay, and also model 1,000 growth conjecture of background and Wang task. So Kamaya shows that profinite completion determined simplest volume and of closed hyperbolic three manifold. And also, so and also Zixi showed that profinite completion detect fiberness of hyperbolic three manifold. Okay, and there are also some other examples, of course. So since our work depends on the work of Witten and Professor Zalewski, so for three-dimensional geometry manifold in the sense of Thurston, the geometry is determined by the profinite completion of its fundamental groups, and in particular, Witten and Professor Zalewski showed the profinite analog of the hyperbolization theorem and the Seifert conjecture by Gabay and maybe Kansa and Jungers. Okay, and also very recently, British Mercury's Reed and Spiller showed that there are some arithmetic lattice here. I mean, so three-dimensional hyperbolic arithmetic lattice with profinite digits in the absolute sense. Okay, and so maybe I should skip something. So, and considering four-dimensional case, and there are very few results here, but the first one is slow. So, profinite flexibility of H2 manifold. So here, I mean, so there are two complex hyperbolic manifold of complex dimension 2, which are not homomorphism, but they have the fundamental groups of them have the same profinite completion. So, and also the three mathematicians show the profinite resistance of flat orbifold among all the closed orbifold with the same geometry. Okay, and also, so I think nowadays, so studies profinite genus of certain flat manifold, or maybe flat orbifold, or maybe flat orbifold. I think I'm sorry, I forgot the okay. And today, and we focus on the problem that for closed orientable for manifold, whether its geometry should be distinguished by its profinite completion, and it's very similar to 3B of Witten and Zalewski. It's 2017 paper in geometry and topology. And so our theorem is that for two manifold, which are closed orientable and four-dimensional with infinite fundamental groups and distinguished geometries x1 and x2. Okay. So here we saw that then they have the profinite completion of them are different if the geometry is not in this set. So in other words, if for example, if M is maybe M is for manifold with geometry three-dimensional hyperbolic times the real line, and N is a four-dimensional hyperbolic manifold, then they cannot have the same completion of their fundamental groups. Okay, but as I have said, so these three types of geometries are more difficult. So we cannot distinguish any pair, for example, HC2, HR4, and HC2 and H2 times H2, and we cannot distinguish these three pairs of geometries with profinite completions of the fundamental of them. Okay, and also for closed orientable for four-dimensional Seifert manifold, and as I have said, it may not diminish any geometry if the base is hyperbolic orbifold, and if the monotomic does not meet certain conditions. However, so we can show its geometry could be detected by the profinite completions of its fundamental group. Okay, so as a result, I said let M and be two four-dimensional Seifert manifold over hyperbolic orbifold, and also we assume they have same profinite completions. And M admits one of geometry. So here there are just two kinds of geometry. It is H2 times E2 or SL2 puta times the real line. Okay, and if and only if N also geometry and they have the same geometry. Okay, in other words, so for a four-dimensional Seifert fibred manifold, whether it admits geometry is determined by the profinite completion of its fundamental group. Okay, so I should remark here, we use the result of Wilton and Zixi about the profinite completions of hyperbolic of three-dimensional hyperbolic manifold groups, and which in turn depends essentially on the development of ego and Daniel Weiss. So in other words, so and in fact our two results here and here is not so difficult, and we use of we use some of the recent breakthrough on three manifold on three manifold groups. Okay, so I think I stop here, and thank you for your attention.
Well, let's thank you very much for your talk. Let's switch microphone and thanks speaker. Right. Well, I have some questions, but I should give first possibility for audience to ask question. If anybody have questions, then please unmute your microphone and ask. I don't see any volunteers, so I will start my questions, then I will ask again. first of all, so you proved for Seifert manifolds that profinite completion does recognize from the manifold being geometric or not, right? It distinguishes geometric manifold from not geometric, those which admit geometry and those which do not admit geometry.
Yes.
But in general, it is possible, or it is unknown, or it is or it doesn't, or what is in general answer for any? Can we, in general, distinguish for manifold which admits geometry and which does not admit geometry?
In general, I'm not sure. So, the reason. So, okay. I think so. Four-dimensional case is more difficult than three-dimensional case, and
Sure.
I mean, so for example, even though to solve whether every so.
I mean, for three manifolds, there is no question because all of them are geometric.
Yes. But in four-dimensional case, there are many of for manifold such that it is orthogonal and its fundamental group is what hyperbolic in the sense of Thurston, in the sense of Gromov. But I think right now we don't have any we don't have enough information on the structure of the group. Yes, since it is not correlated in general.
I see.
So so for example, in the case of three-dimensional, so with the recent result depends on the work of Ego and Weiss. But in the case of two-dimensional complex hyperbolic manifold, it can be solved. The fundamental group of it cannot be correlated in the sense of Ego and Weiss. So in other words, it is so difficult right now. I think.
Okay, my second question is the following. Okay, so your theorem shows that we can distinguish one geometry from the other, and then there is sense to concentrate on every piece of geometry, or meaning take manifolds of certain geometry and to see how they can be distinguished or determined by the profinite completion. For example, starting from most simple one like nil manifolds, Sol manifolds, and so on, right? Do you know? I mean, in these all cases, right? We know that it is they are almost determined by profinite completion, which means that it is only they are determined up to finitely many isomorphism classes. Right, but it is there is no work done for actually calculate these classes or somehow to say what is the exact number.
You mean the number, right?
Number of isomorphism classes in certain.
Yes. What do you mean the number? It is the same sense of the profinite genus, right?
Yes, profinite genus. Yes.
I don't know. So, but I don't know in general, and I don't know the answer. But I think so. In the case of the geometry of H2 times E2 and SL2 times E, I think it should be profinite. No, I have no idea. So
okay.
I have
so then I have the third question. Okay, for this simple manifolds, we know that genus is finite. But for other geometries, do we know it, or it is open question? Like for Seifert geometries, I mean, you listed 19 geometries, all right?
Yes.
There are some other cases where it is clear that the genus will be finite.
No, I think right now there are no answer. I think
no answer. I see.
I think.
Right.
I think no answer.
Okay. So I probably have enough questions. Maybe anybody else have some question?
I have a small question.
Okay, go ahead.
In your theorem, you said that if you consider four manifolds orientable, you could distinguish these two geometries, né, by the profinite completion. Except for four cases.
Yes.
These four cases, why you can not can distinguish? Why the reason? Do you know some reason why they skip you off the list?
But for example, in the case of so yeah, okay. How to say? So for example, for the case of if for manifold here, it admits geometry. It is a four-dimensional hyperbolic manifold, and it is closed by hyperbolic. I mean, it is re-hyperbolic. So even though right now we know, so the free Abelian group of rank 2 J2, it is not a subgroup of the fundamental group of the manifold. But right now we don't know whether J2 is not a subgroup of in the profinite completion of the fundamental group. But in three-dimensional case, it is proved by the paper of Witten and Talisky. But in four-dimensional and the proof also depends on some work of Ego and Daniel Weiss. And but in the case of four-dimensional case, even though the answer of my question above, we don't know. And in my viewpoint, this case is not the most difficult one. And this guy, I mean, it is the complex hyperbolic geometry of complex dimension 2. And we know very few about the fundamental group of 8. And so I think we are very far from understanding the profinite commission of these geometries. Maybe.
Any more questions? I have probably last very naive question. You mentioned the following, that if four manifold admits a geometry, then the fundamental group is residually finite. My question is whether converse is wrong or it is unknown.
Pardon? Yeah. There are some examples of for manifold. Even it is with the Firecall, but the fundamental group of 8 is not residual finite, and it is given by Jennifer Mass.
No. But my question is in the following. Suppose we know that the fundamental group is residually finite. Can we deduce that it admits certain geometry, or it is there is counterexample?
Yes, there are some. I think yes, there are some counterexamples. So
okay.
Yeah, I see. So in all the construction of Mike Davis in 1980s, and there are some of manifold which admits so its fundamental group is virtually right-angled constant group. So it is must be residual finite. But the universal covering of the manifold is not the R4. So in other words, the universal covering of the manifold is very difficult, and then it is different from all for the geometry of the native geometry here. So So in other words, it cannot admit any of the geometries here. Yeah. Okay.
Okay. All right. Thank you very much.
Okay.
Anybody has another question? But let's thank speaker again, right?
Okay.
Now,